This is Lauren, and today I will be sharing my portion of the Brouwer's fixed point theorem project. So to begin, a little bit of history, and I'm gonna try to say these names as well as I can. Luitzenegg Bertus Jan Brouwer is credited with the original idea and proof of Brouwer's fixed point theorem, though many of the ideas we're going to use today to investigate and eventually prove the theorem actually come from another famous mathematician, Henri Poincaré. He pioneered many of the ideas we have today, uh, how we think about like the motion of vector fields and the motion of like points represented by vector fields that are actually useful in a lot of different subjects. So here's Brouwer on the left and here's Poincaré on the right. So Brouwer's fixed point theorem states that any continuous map from the closed disk to itself has a fixed point. And while I was researching the history of this, I came across a fun little anecdotal story. Supposedly, Brouwer came up with the idea to this theorem when he was stirring cream into his morning cup of coffee. He noticed that as he stirred, there always seemed to be a point which didn't move, or like a little particle of liquid that was in the same exact position as before the cup was stirred. And the top of this, if you look at it from this way, kind of represents how we would think of a closed disk in like a two-dimensional space, right? And so I think actually this explanation is a little silly, but also a really good intuitive way of thinking about and understanding Brouwer's fixed point theorem. Moving on, I wanted to go over the fixed point property in general. Here is a definition I stole from my notes. And here are two simple but good examples. So the first one right here, right? This is obviously the graph f of x equals x. Oops. It's harder to type and talk than you think. And so based on the definition, right, f of x equals x, it's pretty clear that every point of this function, right, like every point on this red line is a fixed point, right? So if I look at x equals 1, I get f of 1 equals 1. If I look at x equals 2, I get f of 2 equals 2, and so on for this entire line. So f of x equals x most definitely has the fixed point property. And then looking over here, let's look at the function. This is the function f of x equals x cubed, right? And so I don't know if you remember, but back in I don't even know which class, but I do remember that to solve for a fixed point, we would always set f of x equals to x, just like the definition, right? So I do x cubed equals x, and I would solve that for 0, right? And then I would simplify that. And I will get three solutions to this equation, right? So I get x equals 0, x equals -1, and x equals 1, right? So those are our three fixed points. And if we look at the graph, we can verify those, right? So if I look at 0, f of 0 is 0, f of 1 is 1, and f of -1 is -1, right? So, and there are many mappings or functions like this which don't have fixed points, but since we're dealing with a fixed point property today, I kind of just wanted to do a quick reminder of how we know what a fixed point is and where a fixed point is. So moving on, I wanted to discuss vector fields, which we're going to use today to prove Brouwer's fixed point theorem. So this definition I got right out of our textbook here, and then I created this nice looking easy example of v of xy equals -yx. So, and then let's recall from, I think it would be Calc 3, that a vector field, right? So if I have v of xy, right, we have two components to this, right? This tangent vector, because these are tangent vectors, so they're tangent to a point. or the motion of a point, right? So we have like the f component, right? So we have f of xy, which is the derivative with respect to x, and then we have the g component, right, which is the derivative with respect to y. And these are the two components that comprise each of these vectors. This is what makes them like little tangent lines to the points in this plane. But it's important to know that there are a lot of points like in between these arrows, right? Like these are just the vectors that we drew, right? Like these are just the tangent lines that we drew. And in between these, there are a lot of other points that we're not representing. So this is kind of just like a skeleton version of the vector field, right? And then it's also important to notice that as we move through the vector field, right, there's kind of like this gradual change in the magnitude, right, which is represented by length, and the direction of the vectors, right? So if I look at this one, there's not going to be a vector pointing like this way, you know what I mean? So as we look across this, there's like this gradual change, right, like this gradual motion. And right here in the center, we see that there's nothing, which if vectors right here, right, represent tangent lines to points or motions of points, then it would make sense that things like critical points would show up, right? And it would also make sense that critical points would show up as zero vectors, right? Representing no motion. So critical points are represented as fixed points right here with a zero vector with nothing. So then if we were to take this and kind of like elongate these vectors and make them smaller and just more of them, we would end up getting like this circular motion, right? And it would become clear that all of these points were kind of like moving in like a circular direction, okay? So that's the basics of what we're going to be using vector fields for. Or those are the basic ideas of vector fields that we're going to be using. So then I want to go over what is called the index of a closed curve. And so first of all, I want to clear up. Up here I have written a simple closed curve, right? Because for the purposes of actually proving Brouwer's fixed point theorem, we only need to use a simple closed curve, which is a curve kind of like, oops. It's a curve kind of like this, right? Like something that we could take and deform and it would be the same as a circle, right? So if this is a string, we could take it and kind of just push this edge out and push this edge out, you know what I mean? And push these edges in and we could get like a circle, right? Whereas if we have something like this, in 2 dimensions, I can't really make that a circle, right? So while this is a closed curve, it's not a simple closed curve. Just like this. This is not a simple closed curve. So now we want to think about the idea of placing a curve like this into a vector field like here. So like if I were to place this curve into this vector field here, right? I could look at each of the points along this curve and I could assign to them their respective vector based on, here I want to actually, I think this might look a little better. So yeah, so I could assign to them like their respective vector, right, that kind of just comes off of each point. And because we're thinking of laying this closed curve into a vector field like this, I'm just trying to model that motion, right? Right, so we have a vector for each point, and now this is just like a skeleton representation again, right? So I can't really draw a vector for each point, but you guys know what I mean. So then so remember how we were talking about the fixed point here at the middle, right? Where there's a zero vector and there's no motion? Well, if we're moving in a circular motion here with this closed curve, I think it's pretty obvious that there has to be a point in here that's a fixed point, right? Because we're kind of moving around, you know, we can't just randomly change direction. There's obviously like a circular motion. And then that's the key to finding the index of a curve, right? Is we look at that fixed point and we ask ourselves, how many times did we make a full rotation around that point? So, and that's why I have this example here. I thought that this was a really good way of thinking about it. So, suppose that I'm standing at point P. Like this is like an aerial, like I don't know, like you're up on the roof watching me, okay? and I'm point P, and this is like the path of like an insect that's like buzzing around my head, okay? And I'm standing there and I'm following the insect with my eyes, right? So I'm looking here at it and it buzzes around me and I have one full rotation, right? Then we make a loop-de-doop and I get back to here and I have another full rotation, right? So, and remember, we're counting positively in the counterclockwise direction. So our index number for this curve is 2. And then going off the same idea, it's pretty easy to see that for a simple closed curve, the index can be at most 1, right? Or if I were to reverse these arrows and I went in the clockwise direction, I would have -1. And the same for this, I would have -2 if these arrows were reversed. It's also kind of interesting to know that if I have what's called an isolated critical point, which would be a critical point that's kind of like on its own. It's defined as the only critical point within an open set. Then actually that critical point, so kind of like just like we have here, right? Like if this is like an open set, right? This is the only critical point here. The index of this line right here, this simple closed curve around it, is the same index as that point. So that's another interesting thing to look at. But I think we're ready now to jump into the proof of Brouwer's fixed point theorem.